Welcome to an introduction to equations. Here are our objectives, right? First of all, we want to be able to figure out if a certain number is an actual solution of an equation. We want to be able to solve basic equations of the form x plus a equals something, and then we want to move on to equations of the form a times x equals something, and then finally we're going to finish off by looking at some uniform motion problems. All the skills we're going to talk about today can be translated to more complex equations. We're just going to start with the basics to kind of build those skills. So let's start with figuring out if something is a solution. And this is a good skill to have because anytime you work with an algebraic expression or equation, especially with equations, and you get down to a solution, you want to check your work, which means you need to take that answer, go plug it back into the original equation and make sure it actually works. That's the way to check to make sure you didn't make any mistakes, because if you make a simple mistake, obviously the answer is not going to work. So here are a bunch of just simple equations, right? So this is we're basically reminding ourselves of what an equation means. An equation basically just means is there an equal sign in there or a less than, right? Technically, a less than, a greater than, or a less than or equal to, or greater than or equal to are called inequations or inequalities. But they're still the same thing as an equation, right? It's still something related to something else. You got two sides of an equation. There's some stuff on the left and some stuff on the right, and they're set equal, and you have to solve them, right? That's basically what an equation is. Okay, so here's a simple example, right? We can see that 5 makes the equation true, 7 makes it false. Obviously, 5 is a solution of the equation, and it's actually the only solution for this one because this equation only has one solution. So we're just reminding ourselves of some of the basic properties. Okay, figuring out if -2 is a solution of something a little bit more complicated, well, it still just means plugging it in. And you just got to remember your order of operations. 2 times -2 becomes -4. You add 5 to it, you get 1 on the left. -2 squared is -2 times -2, which becomes +4. 4 minus 3 is also 1. Since 1 equals 1, we see that -2 is in fact a solution of that equation. How about -4 for this one? Do the same thing, order of operations, plug it in on both sides, and you see very quickly that the left side does not equal the right side. So therefore, -4 is not a solution, right? So if you were checking your work this way, you'd go, uh-oh, crap, I did something wrong. Better go double check my work because -4 does not work. Also, sometimes you can get, especially when you have equations that are quadratic or have powers, you'll get two answers and one of them might work and one of them might not. So it's not so much that you did a mistake, but oftentimes, especially with word problems where these things actually model something in the real world, one of the numbers just doesn't work back in the context of the question. So keep that in mind that when you're checking your work, you're not only checking to see if you made a mistake, but you're also checking to make sure that the solution makes sense in the context of the question if you are in fact working with word problems. Okay. What does it mean to solve an equation in the form x plus a equals b? It basically just means simple things where like x plus 2 equals 9. We can see that that's 7, and then it's going to get more and more complicated from there. But it all boils down to the basics of if I have x plus a equals b, don't I just need to subtract a from both sides to solve for it, right? If I've got x plus 2 equals 9, I could subtract 2 from both sides and see very quickly that x equals 7, right? If I've got x plus 6 equals 13, it's the same thing. If I add 4 to both sides, I still have the same solution of 7 because adding something to both sides of an equation does not change the outcome. So this is just reminding us that there are certain things that we can do to both sides of equations and we will still get the correct answer. We can add something to both sides, we can subtract something from both sides, because really, if we're subtracting 5 from both sides, it's the same thing as adding -5, right? So we're right back to, oh, can we add something to both sides? Yes, you can do that. So when we say equations have the same solution, that we call them equivalent equations. In the previous example, x plus 2 equals 9 is equivalent to x plus 6 equals 13 because they both have the same solution of 7. And all that means is when we're doing all of these, what we call legal operations, when we're adding something to both sides of an equation or multiplying both sides by something, as long as it's not zero, and those are legal moves, right? Those legal things we can do, then the resulting equation we get is an equivalent equation to the starting equation that we had. And that's very important because we want to make sure that the answer we get at the end is still an answer for the very beginning, and that wouldn't be the case if these things weren't equivalent equations. So now we're just going to formalize it. The additive property of equations is true, right? We can add something to both sides, and that can be a positive or a negative. So the goal with all equations is to get it down to just your variable equals a constant. And that's how you solve it, right? When you move stuff around and get it down to x equals 6, you now know what x equals. So this is just reminding us that the very last thing we want to do with these things is have x equal something, or whatever our variable is. We want it to equal that. Don't forget that you always want to check your solutions, make sure they work. Here's another simple example, right? X plus 15, you work it out, you get x equals 8. So let's take it up a notch, and now let's look at ax equals b. So what happens if we do the work and instead of getting x equals 6, at the end we get 2x equals 6? Well, duh, we can still see that the answer is 3. But rather than thinking 2 times what equals 6, couldn't we just divide both sides of the equation by 2 and get x equals 3? Yeah, and that's really what you would do with something that's a little bit more complicated. So we're now just expanding it. We're now realizing that if we have something that simplifies to ax equals b, well, instead of having the solution like we do when x equals b, all we got to do is divide both sides by a. Okay, so instead of doing all of this work, we would just divide by 2. But again, we're using this example to highlight some of the things we can do that are legal moves, and that is multiplying both sides of the equation by a number. We already talked about adding. Now we can see that we can multiply because we still get the same answer. So we're basically finding the multiplication property of equations says that as long as c doesn't equal 0, right? I already mentioned that, we can multiply both sides by c, and all is good. And remember, multiplication is the same thing as division. So if we're going to divide both sides by 3, we're really just multiplying by 1/3. So this multiplication property also extends to division. And we can divide both sides by any number, again, as long as it's not 0, because you can never divide by 0. And it's still going to be equivalent, which means the answer we get is still going to be the answer we're looking for the original equation. So if we have something like this, 3/4 z equals 9, and we want to solve for it, couldn't we just multiply both sides by 4/3 to cancel out that fraction, right? We'd multiply by its inverse, basically, and then we get 4/3 times 9, which is 12, and we see that z equals 12. Now, if you have a hard time with this, then I would suggest instead of going straight to multiplying both sides by 4/3, just multiply both sides by 4 to get rid of the fraction, right? Because to get rid of the fraction, you multiply by what's on the bottom. And now all of a sudden, since the 4's will cancel, you'll have 3z equals, well, 9 times 4 is 36. Then you can now divide both sides by 3, right, to cancel this out, and you're going to get z equals 12, right? So it's a couple more steps, but until you get comfortable with multiplying by reciprocals, just do what I always do. Whenever you see fractions, multiply everything by the bottom of the biggest fraction to kill off that fraction, and keep doing it till all the fractions are gone, and then life is easier. Okay, how about another example? Well, isn't 3/4 x, isn't 3x over 4 the same thing as 3/4 x? Right? So you got to remember that when you have things like that, you can kind of pull that constant out in front all by itself, and have this property over here that it's still being multiplied by 3/4. So in order to solve for it, you would, just like before, multiply both sides by 4/3, or you could do it step by step and multiply both sides by 4 to get rid of the bottom, and then divide both sides by 3, but you're going to get the same thing, -12. Okay, how about uniform motion problems? Any object that travels at a constant speed in a straight line is said to be in uniform motion. So you might think, well, uniform motion problems. What the heck are those? Well, they're those things that you always see all the time. Two trains leave Chicago, one traveling west at 40 miles an hour, the other traveling east at 60 miles per hour. How long until they're 300 miles apart? Those types of things. Those are uniform motion problems. Anytime something is traveling in a straight line at a constant speed, it's called uniform motion, right? Constant uniform motion. And when you have uniform motion problems, you just have to remember the key to all motion problems is distance equals rate times time. That's the biggie, right? Distance equals rate times time. So anytime we have uniform motion problems, we're always going to think d equals rt, distance equals rate times time. And all you have to do is solve for what you don't know. They're always going to give you enough information to have two of those pieces. They're always going to give you d and r, and you have to solve for t, or they're going to give you r and t, and you have to solve for d, or and so on and so forth, right? They're always going to give you two of the three pieces. You just need to figure out which two pieces they gave you and how they all fit together. So for instance, suppose a car travels at 50 miles per hour for 3 hours because the rate is 50 and the time is 3, and we know those. We can plug those both in and we can find the distance traveled, and it's pretty obvious, right? 50 miles per hour for 3 hours. You go 50, 50, 50, you've traveled 150 miles, right? That's simple distance equals rate times time. Okay, now what happens when we get those two objects, like those two trains in different directions, or a car and a bike, or whatever it happens to be, in this case, two cars? Well, it's still simple. You still just have to figure out the total distance, the total rate, and the total time. You have to think about what's happening if you click a stopwatch and then you stand up on a big mountaintop and look down on it like you're God or something and watching everything happen. Think of it as like a game board. What's happening? Everything is moving all at the same time, and then if you click the stopwatch again and stop everything, what's actually happened? How much total distance has been covered? How much total time has elapsed? Those types of things is how you figure out distance equals rate times time when there are multiple things moving. For instance, we've got these two cars. They start at the same point and they travel away from each other. One of them is going 30 miles per hour and one of them is going 40 miles per hour. So isn't the distance in between them increasing at a total rate of 70, right? Because think about it. If 1 hour passes, the one car's gone 30 miles, the other car's gone 40 miles, isn't there now a distance of 70 miles between them? 70 miles in 1 hour is 70 miles per hour. So please don't start thinking about, hey, if they're going away from each other, we always add, and if they're going towards each other, we always subtract, because that's not true. So don't try and get patterns like that. Draw a picture, do a quick little let it go for 1 hour, see what happens, and then go, oh, that's what happens. I add in this case. Or in another example, you'll do it and you go, oh, I subtract in that case, okay? So don't start to, simplify too much, because you will make mistakes. Okay, how about this? We've got two things coming at each other. So you've got a total distance of 800 miles, right? And in 1 hour, one plane's going to cover 350 miles. The other one's going to cover 450 miles. So in that 1 hour, aren't they going to become 800 miles closer to each other? So now, do you see that you add? Even though they're coming at each other, you add. So we added when they were going away from each other. We added when they're going towards each other. So you got to watch out for these patterns, right? So draw a picture and figure it out. Look down on it like a game board. And okay, in 1 hour, this one's gone 350 miles, this one's gone 450 miles, and they both are going towards each other. So they've closed the gap. So the total distance between them has shrunk by a total of 800. Oh, so I'm adding their rates. How about this? We've got a boat in the river. This is a common one, right? You've got a boat going with the current or a boat going against the current. Well, if the boat is going with the current, every hour its engine pushes it forward 10 miles, but the current also pushes it forward 4 miles, and it covers a total of 14 miles in 1 hour, so its rate is 14 miles per hour. But what if it's going against the current? In 1 hour, its engine pushes it forward by 10 miles, but the current pushes it backwards by 4, so you take the difference, 10 minus 4, and you get 6. So here's an instance where you've got two things kind of going at each other, right? We had the two planes flying towards each other, and we added. But here we've got two things coming towards each other. The current is going to the right, the boat's going to the left, and yet we don't add, right? In this case, we subtract. So that's why I say it's tough to try and come up with patterns for the direction equals addition or this direction equals subtraction. Nope. Draw a picture, let it go for 1 hour, figure out what happens, and then that will give you your new rate. So that's kind of the trick, the technique is always let it play out for 1 hour and then ask yourself what's happened. How far has things changed? And that will help you figure out if you're going to add the rates or subtract the rates. Okay, let's put it all together and see if we can look at one example where we've got two cyclists start at the same time at opposite ends of an 80-mile course. One cyclist is traveling at 18 miles per hour, the second is traveling at 14 miles. How long after they begin cycling will they meet? Well, if they're at opposite ends, aren't they coming towards each other, right? And they start 80 miles apart. So let's, start the stopwatch. 1 hour later, the first one has gone 18 miles, the second one has gone 14 miles. So hasn't the total distance in between them been, taken down? They've gone 18 plus 14. They've done a total of 32 miles towards each other, right? They're 32 miles closer. So isn't the distance covered 32 miles in that 1 hour, which means their combined rate is now 18 plus 14 or 32 miles per hour. So now we know their rate. We know the total distance is still 80. So 80 equals 32 times t. Solve for t. Divide both sides by 32, and you see that it takes 2.5 hours until they meet. Excuse me. And then, knowing that, you could answer any other question like, where on the track do they meet? I.e., how much distance does each person travel? And you go, well, the first one did 18 miles per hour, so you do 18 times 2.5, and that's how far they traveled. And the other person did 14 times 2.5, and that's how far they traveled. Okay, so uniform motion problems are very easy if you draw a simple picture, and a simple picture is just arrows. You don't have to, draw all these fancy boats and airplanes and stuff. It's just an arrow. There's one airplane on the left that's going to the right and one airplane on the right that's going to the left, and label them. 350 on the left, 450 on the right, and then figure out whether you're going to add those rates or subtract those rates by letting it go for 1 minute and figure out what the cumulative distance traveled in 1 minute is. That's the key.